So we've been dealing with redox reactions at the standard state, right? So we see standard cell potentials, right? And we've been using your table of standard reduction potentials. Everything is in standard state. But of course, when you perform an experiment in the laboratory, most of the time, it will not be in the standard state. First and foremost, you will be using concentrations that are not equal to 1 molar, right? So again, the definition of standard state for aqueous solutions is that your solute has a concentration of 1 molar. So if the concentration is not 1 molar, then it's no longer in a standard state. So it's what we call a non-standard state. So we've seen this reaction class, which is the displacement of copper 2 ions by solid zinc. So if you look back in the previous videos, you will recall, or maybe you've written it down in your notes, that for this reaction at standard state, you have a standard cell potential of 1.103 volts. Okay? But if you change the concentrations of your ions involved in the redox reaction, for example, you used a copper 2 solution with a concentration of 2 molar, and you use a zinc solution with a concentration of 0.1 molar, and you measured the voltage of that cell, you will not get 1.103 volts. So if you use these concentrations, you will get a different measurement of the cell potential. And this is how they came up with the conclusion that your cell potential is actually a function of concentration. So again, before this part of our lesson, everything that we have treated are standard states or redox reactions at standard states, okay? But what if they are no longer in the standard state? So we need to have a new equation that will give us the cell potential in a non-standard state. So just as a refresher again, for this reaction, what you have is your zinc ions in the anode, or your zinc electrode as your anode. So this is 0.10 molar plus 2 electrons. And you have your copper electrode as your cathode. So you have copper 2 ions with a concentration of 2 molar plus 2 electrons producing solid copper. Okay, so adding the two half reactions, we get this. Now, again, we can write an equilibrium constant expression for this reaction. And what we have is concentration of zinc over the concentration of copper 2 ions. But again, this is no longer in a state of equilibrium, right? It's no longer in a state of equilibrium because it's in a non-standard state, right? So this is actually your reaction quotient, okay? And then recall, class, that we have this relationship between delta G and delta G naught. Again, this is delta G at standard state. We have delta G equals delta G naught plus RT ln Q, where Q is your reaction quotient, right? And then delta G naught is equal to negative NF standard cell potential. We can also write a counterpart formula wherein what we have is just the non-standard state potential. Your cell potential in a non-standard state. Okay, so that's without the not symbol. Plus RT ln Q. So dividing the whole equation by negative NF, we have E cell equals standard cell potential minus RT over NF ln Q. So for this particular redox reaction, we replace Q there with the expression. So that's E cell equals E naught cell minus RT over NF, Ln concentration of zinc ion over concentration of copper 2 ion. And this one, class, is what we call the Nernst equation. And the Nernst equation gives us the relationship or the dependence of your non-standard state cell potential to the concentrations of your ions involved in the redox reaction. So again, you have the Nernst equation here. So for example, class, for this particular cell, with the given concentrations, we can compute for the cell potential. So again, your standard cell potential is positive 1.103 volts. Saan to galing, class? Yung pwede mong i-compute using the table of standard reduction potentials. And then R here is 8.314, your universal gas constant. Tapos you have temperature not indicated, so we will use 25 degrees Celsius or 298.15 Kelvin. Let me rewrite that because I don't have enough space. So E cell is equal to positive 1.103 volts minus 8.314 joules per mole per Kelvin times 298.15 Kelvin over 2, the electron number is 2 as seen here, times 96,485 coulombs per mole. Ln, concentration of zinc is 0.10 molar. Concentration of copper is 2 molar. So the cell potential for this setup is 1.103 minus 8.314 times 298.15 over 2 times 96,485 times Ln 0.10 over 2. Okay, so we have 1.1414. So that's our computed value, 1.14148. So a bit different from what is indicated by my reference, 1.142. But still, we see here how the Nernst equation is used to get your non-standard state or non-standard cell potential. Okay, so again, cell potential, non-standard, is a function of your concentration. Okay. Again, class, we can simplify your Nernst equation just by plugging in your constant, so your R and your F or Faraday's constant, and setting the temperature to 25 degrees Celsius. So you can write another form of your Nernst equation, which is E cell equals E naught cell minus 0.02569 over N times ln Q. That's correct, right? 8.314 times 298.15 divided by 96,485. 0.02569 here. So you can also use this form of your Nernst equation. Okay, so it's Q class, not K. So it means that for redox reactions, we consider your redox reactions at standard state. They are in a state of equilibrium. Okay? So let's move to the next slide and practice using your Nernst equation. So what is the value of the cell potential for the voltaic cell pictured below and diagrammed as follows? Although in the picture, we already have the voltage, but let's see if the computed or the calculated cell potential will match the one displayed in the figure. So we have actually we must have access to our standard reduction potential table. Let's just scroll back to that slide with the standard reduction potential table. Okay, so our formula is E cell equals E naught cell minus RT over NF ln Q. Okay, so according to the diagram, our anode involves or our anode reaction. Okay, let's write our anode reaction. We have iron 2 losing 1 electron forming iron 3. So this is our oxidation half reaction. And then in the cathode, what we have is your silver ions gaining electrons to produce solid silver. Okay? And there's no need to write coefficients because there are the electron number for the half reactions are equal. Okay, so let me go back to a few slides just to get the standard reduction potentials of these half reactions. So iron 3 to iron 2, that's the reverse of this reaction. Standard reduction potential is positive 0.771 volts. And for our cathode, that's silver. So that's positive 0.800. Okay, we've taken note of that. Let's go back to our slide. So why did we get the standard reduction potential values? Because we need to get the standard cell potential. It's needed in the formula. So that's cathode minus anode equals that's 0.8 minus 0.771, 0.029 volt. Okay. So, okay. Now, in our Q, in our reaction quotient, which is in the numerator, which is in the denominator. So we see here from our reaction, we have iron 3 as a product, and we have iron 2 and silver ion as reactants. So now, let's go to our Nernst equation. So we have 0.029 volt minus 8.314 joules per mole per Kelvin times 298.15 Kelvin over 1 times 96,485 coulombs per mole. Ln, so product is iron 3, so the concentration is 0.20 molar. And then reactants, we have iron 2 with a concentration of 0.10 molar and silver ion with a concentration of 1 molar. So now, let's compute for the cell potential. So 0.029 minus 8.314 times 298.15 over 1 times 96,485 times ln 0.20 over 0.1 times 1. So we get a value of 0.0111922 volt. So that matches the one in the figure. So this is the cell potential of this cell, voltaic cell. So again, it's voltaic because your cell potential is positive. So the reaction is spontaneous. Okay? Next. I think there's another problem here using the Nernst equation. Okay, so will the cell reaction proceed spontaneously as written for the following cell? So we have a silver electrode and a mercury electrode. So this is our anode, this is our cathode. And we have the table here, which means let's go first by writing our half reactions. It's a good practice class. So I highly suggest, wag niyong titigan yung problem. Wag niyong titigan yung given that everything is inside your brains. Because the brain is very tricky. It has a lot of neural connections na yes, nandito sa utak, pinaprocess niyo sa utak, but there will and will always be some neural connections that will disturb your train of thoughts, your process, kung paano nyo pinaprocess yung problem. Isulat nyo. Isulat nyo. Okay? So, write the anode reaction. So, that is solid silver being converted to silver ion and losing 1 electron in the process. And then, for our cathode, so it's the reduction of mercury 2 gaining 2 electrons and being transformed into liquid mercury. So this I have to multiply, excuse me, by 2 to make the number of electrons equal. So we have 2 silver plus mercury, and then 2 silver ions plus liquid mercury. Okay? So now let's look for their standard reduction potential. So for silver, this is positive 0.800 volt. And for mercury, let's look for mercury. Meron bang mercury dito? Is there mercury? Oh, wala siya dito. Okay. Let me just jump a bit to my reference to look for the standard reduction potential of mercury 2 ion. Okay. Okay, for mercury 2, okay, the standard reduction potential is 0.854. It's not here, right? Hindi man ako nabubulag, di ba? Minsan kasi na-overlook ko yan eh. Wala siya dito. So, it's 0.854. So, positive 0.854 volt. So, now let's compute for the standard cell potential. That's cathode minus anode. So, 0.854 minus 0.8, which is 0.054 volt. So, now let's go to our Nernst equation. So, E cell is equal to E naught cell minus RT over NF ln reaction quotient, which is equal to concentration of silver ion squared over concentration of mercury 2 ions. So you see here, class, the significance of writing the balanced redox reaction, because you need to be able to write your reaction quotient correctly. So, kung hindi nyo siya binalance at diniretso nyo lang, ayun, mali na kasi dapat may exponent na 2 si silver ions. Okay? So, let's plug in our values. We have 0.054 volt minus 8.314 joules per mole per Kelvin times 298.15 Kelvin over 2, the electron number is 2, times 96,485 joules per mole per Kelvin, Ln. So concentration of silver is 0.075 molar squared over concentration of mercury is 0.85 molar. Okay, so the cell potential is, let's compute for that, minus 8.314 times 298.15 over 2 times 96,485 times ln 0.075 squared over 0.85. Okay, so we have a cell potential of 0.11846 volt. So what is our conclusion? Since the cell potential is positive, we have okay, the cell potential is positive. So it means that the reaction is spontaneous, and that's because you will get a negative delta G, not delta G naught. You will get a negative delta G value. And that points to the fact that the reaction is spontaneous. Okay, so it will proceed as is without any external source of energy. Okay. So in connection to your Nernst equation, we will now take a look into the applications of your electrochemical cells. So saan ba sila ginagamit? Okay? So I've already mentioned class about batteries, and we will actually go a bit into that in a while. Pero dito muna tayo sa medyo nasa technical side pa ng application, but I'm sure you will appreciate this. So first, let's go to concentration cells. Okay? When we say concentration cells class, if you take a look at the setup here, you will notice that you have the same anode and you have the same cathode. Pareho lang yung electrodes mo sa anode at sa cathode. Ang nag-iiba lang ay yung concentration ng solutions. But you have the same. You have the same reaction taking place in the anode, tapos yung nasa cathode yung reverse lang ng reaction sa anode. Right? So here we see two standard hydrogen electrodes. Well, it's the first one, the one on the anode is not actually standard because the concentration is not 1 molar. So the concentration of your hydrogen ions is not 1 molar. But the one in the cathode is a standard hydrogen electrode. But the thing here, class, is that the reaction in your anode is the reverse of your reaction in the cathode, which means that they will essentially cancel out. So, anong ibig sabihin nun? So, sa anode, ang reaction natin is, so you have your H2 gas getting oxidized to hydrogen ions. So, you lose 2 electrons. And then, in the cathode, it will be the reverse, which is you have 2 hydrogen ions gaining 2 electrons, forming hydrogen gas. But again, class, the difference is that in the anode, you have X molar concentration of your hydrogen ions. In the cathode, you have 1 molar concentration of your hydrogen ions. Now, the thing is, basically, class, ang nangyayari dito is you get so hydrogen ions in your cathode going, quote unquote, to your anode. Okay? So, parang ang effect niya, class, is dilution of the electrode with the higher concentration and an increase in the concentration of the other. So, ang mangyayari dito is bababa yung concentration ng hydrogen ions mo sa cathode, tataas yung concentration ng hydrogen ions mo sa anode until they become equal. So essentially, para ka lang naghalo ng dalawang solutions ng hydrogen ions. That's the overall effect of a concentration cell. However, class, okay, ito yung gist dito. Okay. Since you have the same reactions or you have reverse reactions taking place, your standard cell potential is equal to 0. Magzi-zero yan, di ba? Kasi they are just reverse of each other. But since this is in a non-standard state, meron ka ma-measure na cell potential. Right? So using your Nernst equation, so you have here E cell equals E naught cell minus RT over NF times Ln. So if we look at the balance reaction, you have X molar in the numerator and 1 molar in the denominator. E naught cell is 0 kasi nga reverse reactions lang yung nasa anode and nasa cathode mo. But you still measure a certain cell potential because of the difference in the concentrations of your ions in the two electrodes. Okay? So for example, class, let's try to solve this one. So you have a concentration cell made of copper electrodes. So para masanay lang ulit tayo, class, ano ang nasa anode natin? You have solid copper transformed into copper 2 ions whose concentration is 0.050 molar plus 2 electrons. And then in the cathode, you have copper 2 ions with a concentration of 2 molar, gaining 2 electrons, and the product is solid copper. So again, ang effect ay yung may mas mataas na concentration ang nasa reactant side natin and yung may mas mababang concentration ang nasa product side. Okay. So we have E cell equals E naught cell minus RT over NF Ln 0.050 molar over 2 molar. Again, this is equal to 0. The standard cell potential is 0. But what is the cell potential? So that is negative 8.314 joules per mole per Kelvin times 298.15 Kelvin over 2, the electron number is 2, times 96,485 coulombs per mole. Ln 0.050 molar over 2 molar. So what is the measured cell potential? So let's compute. 8.314 times 298.15 over 2 times 96,485 times Ln 0.050 over 2. So we get a cell potential of 0.047386 volt. So, meron pa rin siyang cell potential kahit na walang net reaction. So again, yung overall effect lang niya is parang pinaghalo mo lang yung dalawang solution. So eventually, magiging equal yung concentrations nilang dalawa. Okay. So, Another important application of these voltaic cells is the measurement of your KSP. So you learned about KSP a few weeks ago. So this is your solubility product constant for your slightly soluble salts. So typically, ang setup niya is you have one electrode in which you have a saturated solution of your slightly soluble salt. So for example, we have a concentration cell here. Concentration cell siya. So ibig sabihin, yung reaction mo sa anode ay reverse lang ng reaction mo sa cathode. But because of the difference in the concentrations, you have a measured cell potential. So in your anode, you have here a saturated solution of silver iodide. So meron ka nung silver, 'di ba? Kasi kailangan may equilibrium siya with the solid. And you have your silver electrode there connected to your cathode. So you have your silver electrode and a solution of silver ions. So dapat hindi rin siya saturated solution. Kasi wala kang mami-measure na potential, 'di ba? Kung parehong saturated solution yan ng silver iodide, then zero ang cell potential niya. Okay? So this must be a solution of one of the ions with a different concentration. So a solution of silver ions will suffice. So let's say galing siya sa silver nitrate. So silver nitrate is soluble in water. So silver, tapos yung nitrate ions mo, spectator lang sila. Okay, so for this one, so you have the setup there. Ang nasa anode natin ay silver solid, and then you have silver ions. And this is part of your saturated silver iodide solution. And then in the cathode, you have silver ions with a certain concentration, such as 0.1 molar. And then this gains 1 electron, producing solid silver. Okay, so the net reaction is you have silver ions in your cathode as your reactant and silver ions in your saturated solution as your product. So from here, how can we measure KSP? Recall that when you learned about KSP, so let's write the dissociation of silver iodide. When you learned about KSP, you related it with solubility, right? So if S is the solubility of silver iodide, then in the solution, you have S concentration of silver ions and S concentration of iodide ions. So KSP is written as the concentration of silver ions times the concentration of iodide ions. In terms of solubility, KSP is equal to S squared, which means through this concentration cell, you can get the concentration of silver ions. That is your S. You can get KSP. So once you have set up your cell, your concentration cell, you can measure your cell potential, and using the Nernst equation, you can get the concentration of your saturated solution. So Nernst equation. So E cell equals E naught cell minus RT over NF ln. Concentration of silver ions in the saturated solution over concentration of silver ions in your cathode. This is again equal to 0. Your measured cell potential is 0.417 volt equals negative 8.314 joules per mole per Kelvin times 298.15 Kelvin over 1, electron number is 1, times 96,485 coulomb per mole. Ln, this is our unknown, or the concentration of silver ion in the saturated solution, divided by 0.1 molar. So let's solve for the concentration of silver ions in the saturated solution. Okay, so negative 8.314 times 298.15 over 96,485. 0.417 divided by that value, inverse of ln, times 0.1. So the concentration of silver ions in the saturated solution of silver iodide is 8.93 times 10 raised to negative 9. So this is also S. This is the solubility. So now to evaluate KSP, we just need to get the square of 8.93 times 10 raised to negative 9. So KSP of silver iodide is equal to 7.975 times 10 raised to negative 17. So recall that your KSP values are small values. So our answer makes sense because it's in the magnitude of 10 raised to negative 17. One more example. So for silver chloride, the KSP is 1.8 times 10 raised to negative 10. What would be the measured cell potential for the voltaic cell if the contents of the anode half cell were saturated AgCl and solid AgCl? So this refers to the same setup, but we just replaced the anode. So how will the setup look like? It's the same. So you have there your silver chloride solution, and you have your silver chloride solid, then you have your silver electrode, and so on. So it's the same setup. We just replace the solid and the saturated solution. So now we need to get the concentration of our saturated silver chloride solution. So again, it's silver chloride solid dissolving or dissociating into aqueous silver ions and aqueous chloride ions. So KSP is equal to concentration of silver ions times concentration of chloride ions. Again, if S is your solubility, then at equilibrium, you have S molar of silver ions and S molar of chloride ions, where S is your solubility. So we have 1.8 times 10 raised to negative 10 equals S squared. So S is equal to 1.34 times 10 raised to negative 5. So this is the concentration of your silver ions in the saturated solution. Let's go to the Nernst equation. So cell potential equals standard cell potential minus RT over NF, Ln, concentration of silver ions in the saturated solution, over 0.1 molar. This is 0. So that's negative 8.314 joules per mole per Kelvin times 298.15 Kelvin over, what is the electron number? It's 1 times 96,485 coulombs per mole times Ln, 1.34 times 10 raised to negative 5 molar over zero point 0.1 molar. So the value that we will get is the measured cell potential. So we get a value of 0.2291 volt. So that will be the value that your voltmeter will give for this concentration cell. Okay. Another application, I will discuss it shortly, which is measurement of pH. But before that, we learned about the standard hydrogen electrode, right? So it's the reference electrode, and that's why we came up with the standard reduction potential values. However, your standard hydrogen electrode, although it was chosen as the reference electrode, it's actually not practical because number one, it uses combustible hydrogen gas. So relatively, because it's combustible, it's very unstable. So there were other standard electrodes that were um, constructed. So instead of the standard hydrogen electrode, these standard electrodes are used for more practical setups. But again, your She or the standard hydrogen electrode is the one assigned with a potential of 0. These alternative standard electrodes, their potentials are not equal to 0. Okay, so first we have the silver-silver chloride electrode. So this is the diagram, and this is the half reaction in your silver-silver chloride electrode. And for this one, the cell potential is given as 0.22233 volt. So this is if you couple this silver-silver chloride electrode with your standard hydrogen electrode. That is why your half reaction is a reduction half reaction. For the calomel electrode, this uses mercury, liquid mercury, and mercury 1 chloride. So the half reaction is shown here, and an electron is missing on the reactant side. There should be an electron here. So that's another reduction half reaction because it's coupled with your She. After you couple it with your She, its standard reduction potential is 0.2680 volts. And then finally, there's the saturated calomel electrode, which is just your calomel electrode, but instead of using a 1 molar solution of chloride ions, it uses a saturated solution of chloride ions. And for this one, it has a standard reduction potential of 0.2412 volt. So these are the typical reference electrodes used for more practical contexts wherein your standard hydrogen electrode is not very applicable. It's not very advisable to use. Okay. Now, these electrodes, specifically your saturated calomel electrode or your silver-silver chloride electrode, they are typically used in your pH meters. So they are used in the measurement of pH. Now, for the measurement of pH, there is the so-called glass electrode. Okay, the glass electrode, its features include a thin-walled glass bulb on one end. So if you have seen a pH meter, you will notice that on one of its ends, specifically the end that you dip into your liquid sample, it has this bulb. And this bulb is actually made of a very, very thin wall. And this allows contact of the solution inside with the solution of your sample or with your sample itself. And this is essential because the pH meter needs to sense the amount of hydrogen ions in your liquid sample. And aside from this, typically it has the silver chloride standard electrode. And then inside this glass electrode is also a hydrochloric acid solution of known composition. For example, it's set to 1 molar. Now, the measurement of pH by your glass electrode is based on the concept of your concentration cell, as we will see in a short while. And then, aside from your standard silver chloride electrode, there is another reference electrode inside. So the glass electrode has 2 electrodes inside. Okay, so aside from the silver chloride, pwedeng meron pa siyang isa pang silver chloride, or the reference electrode can be your saturated calomel electrode. Okay, so what happens inside your glass electrode? So for us to have an idea, here is the cell diagram. So you have your silver chloride standard electrode. And then you have the glass membrane. So that's the glass bulb. And you have your hydrochloric acid. This one is your liquid sample. So the hydrochloric acid of known solution is here, reflected here in this part of the cell diagram. This one is your sample, the one whose pH you are measuring. And then you have your reference electrode. Baliktad pala. Ang reference electrode ay yung nasa anode. So this is your reference electrode, and then you have your standard electrode in the cathode. So what are the reactions taking place? So here are the half reactions. So you have the oxidation of silver. So your solid silver loses 1 electron, so it forms the solid silver chloride. That is what is happening in the anode. But in the cathode, the reverse reaction takes place. So you have solid silver chloride getting reduced to solid silver and chloride ions. So these two reactions will just cancel out. But again, you have unequal concentrations of your hydrogen ions. So yung hydrogen ions natin in your hydrochloric acid solution inside the reference electrode. So that's found in the reactant side. And you have the concentration of hydrogen ions in your liquid sample. So that's in the product side, which means we can write a Nernst equation for this one. So we have E cell equals E naught cell minus RT over NF ln concentration of unknown, which again is your liquid sample, over 1 molar. Now, since we have the definition of pH as negative logarithm of hydrogen ion concentration, it's more convenient if we convert this ln to logarithm. So to convert that, we just need to introduce a factor of 2.303. So this is 0. So the factor is, that's negative RT over NF times 2.303 logarithm of hydrogen ion concentration. Okay, so to simplify the formula, we can plug in the values of the constants, and your electron number is 1. So that's negative 8. Actually, I would like to place the negative sign here. So we have 8.314 joules per mole per Kelvin times 298.15 Kelvin over 1 times 96,485 coulombs per mole times 2.303 times negative logarithm of hydrogen ions. Which means, so let's simplify the factor here. That's 8.314 times 298.15 times 2.303 over 96,485. So we have 0.2 0.05917 times pH, because this is equal to pH. So this is the formula for your glass electrode. So once you have the cell potential measured by your glass electrode, you can get the pH value using this formula. And because of this, after the construction of your glass electrode, which specifically detects or senses hydrogen ions, after that, the construction of these so-called ion selective electrodes took place. So you can actually construct any electrode that can detect or sense a specific ion, such as sodium, ammonium, potassium, chloride, calcium, etc. Just like how your glass electrode was constructed. So your glass electrode was the predecessor of these ion selective electrodes. Wait, now since we are talking about applications, we will now go to batteries. So I will just discuss one type of battery, but let's discuss or let's define first the general types of batteries. So there are what we call primary cells. So primary cells are those whose chemical reactions are irreversible. So these are your disposable batteries, your one-time use batteries. And you have your secondary cells. So the chemical reaction taking place inside these secondary cells are reversible. So you can recharge these batteries. And we also have flow batteries and fuel cells. So these flow batteries just need a supply of a certain electrolyte, and this electrolyte will pass through the battery, and the chemical energy stored in your electrolyte will be converted to electric energy. So we will discuss primary cells. So first, let's go to the dry cell, or the Leclanche dry cell. And it's called dry because there is no free liquid present. Although you have a paste inside, but you don't have a liquid state component. So the electrolyte is a moist paste of manganese oxide, zinc chloride, ammonium chloride, and carbon black or soot. These dry cells, the one that uses this electrolyte, have maximum voltage of 1.55 volts. The oxidation half reaction is simple. It's just the oxidation of your zinc. But the reduction half reaction is a bit more complicated. So um, in essence, the reduction half reaction taking place is this one, which is the reduction of manganese oxide. This is manganese 4. From manganese 4, it became manganese 3. So that's a reduction in the charge of your manganese, right? So this one produces a basic solution. However, because of the presence of the ammonium ion, so the ammonium ions can actually react with the hydroxide ions produced by the reduction half reaction, and this creates ammonia gas. Now, the ammonia gas can actually interfere with the voltage output of your dry cell, and this lowers the efficiency of this battery. And to prevent this, your zinc ions actually form a complex ion with the ammonia gas. So it produces this solid compound. However, another problem arising from this one is the electrolyte medium is actually acidic. So aside from the buildup of ammonia gas, this paste is acidic. So it's because you have ammonium chloride. So because of the acidity, the zinc metal can actually react with the acid, as we have seen, right? Most metals react with acid. And this also adds to the decreased efficiency of this dry cell. So to solve this, they came up with what is called the alkaline cell. And we typically see these. So ito yung mga common batteries na ginagamit natin. So the alkaline cell uses a base instead of ammonium chloride in the paste or the electrolyte medium. So you have either sodium hydroxide or potassium hydroxide. You have the same oxidation, you have the same reduction half reaction. And then you see there the same oxidation half reaction. But the difference is that the zinc ions produced in your oxidation half reaction react with the generated hydroxide ions in your reduction half reaction. So you create this solid zinc hydroxide. And because of this, you don't have a buildup of ammonia gas, and zinc also does not dissolve because the medium is basic instead of acidic. Okay, so um, that will be the coverage of the applications of your voltaic cells. And for the next topic, it will be electrolysis, and we will discuss this in the next video.